Hello everyone, welcome to Vedantu JEE English channel. This is your Madhan, your Big B and Physics coach. Today we are going to be discussing KTG and tomorrow we'll be completing thermodynamics. KTG and thermodynamics put together, there is a possibility of 2 questions in 2025. Possibility, right? I strongly believe that 1 question for sure is going to come as the number of questions have got reduced. But yes, there is a chance for 2 questions for sure, right? If you can hear me, if you can see me, please say clear. If you can hear me, if you can see me, please say clear. We'll start with the lecture. Good evening, Sanjay. Good evening, Bhargavan. Good evening, Sadia, Sultana. Good evening. If you people can hear me, please say clear. What about semiconductors part 2? Sadia Sultana, see, what happened? I think the thumbnail was put as PYQs of semiconductors or something, but actually I have completed in that only. I think the thumbnail was put as PYQs of semiconductors, right? In that itself, what I have done was I was actually doing semiconductors along with the PYQs. So the second part of the semiconductors is in that. Please check in that. Right? It was the thumbnail issue. Okay. Super. We have many people live today. Might be the chapter is something which is creating a lot of interest for them. Okay. Now, there is a crash course which has started, right? I hope all you people know that. And there are some long-term batches also, like 6 months of batch and all those things. So this is a slide for the crash course. But if you are interested in that 6 months of courses and all that stuff, you can enroll into Vedantu website and you have those things. You have those links available. You can buy from there. Okay. Now, we will just move to kinetic theory of gases. Before we start that, we are going to take some assumptions. What are those assumptions? Let us discuss all those things. Yes, one second, everyone. Yes, we are dealing with kinetic theory of gases. There is a question which is asked by Balaji. Next week is going to be wave optics. And mechanical properties of solids. So how many questions you people can expect from this chapter, or you can say from this lecture? There is high possibility of 1. From tomorrow's lecture, there is high possibility of 1. Both of them put together, definitely you will have 1 question and high possibility of 2 questions. Why? If the paper is of 30 questions, I would have mentioned, if the paper is of 30 questions, I would have clearly mentioned that KTG thermodynamics put together would have been 2 questions for sure, but the number of questions have become 25 now. As a result, I expect strongly 1 question. If you are lucky, you will have 2 questions. Okay, fine. Now, what are these assumptions? First of all, minimum there should be 10 to the power 23 molecules per centimeter cube. Only then the assumptions whatever I am going to give are going to be holding good experimentally, right? Whatever the assumptions I am going to give, some of them are going to be universal, some of them are going to be holding good. If you are going to take minimum 10 to the power 23 molecules per centimeter cube, look, if you take this, then density at every point can be taken constant. Density at every point is taken constant. But for that to happen, as I said, you have to take more than 10 to the power 23 molecules per centimeter cube. And one more thing is that pressure at every point is taken to be constant. Even this is also going to be happening if you have these many molecules. Otherwise, the pressure on the walls of the container and pressure inside also at every point is going to be changing slightly. As the number of molecules keep increasing, that change in the pressure is going to be keep decreasing. If the number of molecules is so big, then the pressure is also going to be attaining a constant value. I'll show you that. I'll show you that. For example, look here. See, I have taken, this is a free thing, phet.colorado. This is one simulation thing. A lot of physics experiments are going to be there. A lot of good physics experiments are going to be there. And one more is going to be Walter Fend. Even that, it's a old one, developed, I think, by German scientist, right? So German physicist. So that person also has good simulators. And one more simulation I have taken. So look, here we have a pump. What I'll do is I'll choose blue, which is heavier one, right? Then I take this pump up, and then when I am going to be pumping some gas into it, you can see all those heavy molecules, gas molecules, they have entered, and look at the pressure. What is happening to the pressure? Can you see that the pressure is changing? And by now, you people already know in chemistry or thermodynamics, all these gas theories have been done in chemistry. They would have taken the pressure to be constant. Man, if the number of molecules are finite, the pressure is going to be changing. Have you noticed? So if the number of molecules is going to be big, that's when the pressure is going to be almost constant. Mr. Vineet, we are going to be completing the syllabus very soon. I think next week I'll be doing wave optics and all those things, right? After that, I think only fluid mechanics will be left. That will be taken care by Shreyas sir. With that, the syllabus will be completed. You'll have everything in the road series. Okay. Now, you can clearly see that the pressure is something which is continuously changing. And look at the movement of the particles. Some of them are moving faster, some of them are moving slow, and they keep on changing their directions. So basically, they are making collisions also over there. Right? So let us go back. Let us go back. Now, as I said, pressure at every point is taken to be constant. That will come out to be automatically constant if the number of molecules are too big. Okay. The next thing. What is the next thing? See, gas molecules are taken to be very small in size such that they won't occupy much of the volume. Very small in size such that the volume occupied by them is negligible. Volume occupied by material of gas. Material of gas is negligible. Material of the gas is negligible. That means matter of the gas molecules. Matter of the gas molecules. Okay. Next, they are taken to be spherical. They are taken to be spherical, rigid, and elastic in nature. And whatever the collisions they are going to be making, they make perfect elastic collisions. They make Afifa Muhammad Ali, one second, one small, I won't break the flow from now. Every 15-20 minutes, I'll look at the chat. So, Sir Shreyas sir said he wouldn't take fluids. Actually, we had a discussion today. I can't take fluids. I teach in Vedantu Telugu JEE platform also. On that platform, I am going to be doing fluids in the second week or third week of what we call December, right? So what I have done was, those who have enrolled for the paid batch, on their demand, I was doing the fluids in that batch. So once the fluids is done in the paid batch, only then I can do it on the free platform, that is going to be YouTube. As I have already given my word to the Telugu community, so to keep up my word, I shouldn't do fluids anywhere. That's the reason why we had a discussion and I said to Shreyas sir that I can't do fluids. So that's the reason why I was given wave optics for the next week, right? Okay. And in fact, I'm having a very hectic schedule. From December first week, my load is going to become so bad that actually we are also having a discussion like how to manage and all those things. You'll be updated. You don't worry. You'll be updated. You don't worry. Okay. Now I'll just focus on the teaching part. 15-20 minutes. I'll just look at for every 15-20 minutes, I'll look at the chat. So don't spam the chat. Even if you spam the chat, 15-20 minutes, I'm not going to look at it. Right? So, okay. Now look. They are going to make elastic collisions, man. So what is the advantage of, or what you are going to get from these elastic collisions? So what we are going to get from those elastic collisions is that, for example, we have the wall of the container and we have a gas molecule which is going to be coming towards the wall, let's say with some v speed. After collision, it should bounce off, right? So after collision, let us take that it is going to bounce off with a speed v1. So what is the coefficient of restitution? Coefficient of restitution is going to be velocity of separation by velocity of approach. Velocity of approach. Now, what is the coefficient of restitution? E is equal to 1. And velocity of separation. Now look, from the colliding surface, this particle after collision is separating with how much velocity? v1. By approach, before the collision, the particle is approaching the collision surface with how much speed? v speed. So from here, v1 is going to be equal to what? v. This is what you people should know. So whenever a gas molecule is going to be making collision with the wall, with how much our speed it is going to be colliding, with the same speed it is going to bounce back. Okay, now look. So they make elastic collisions, that is also done. Now, whatever the intermolecular force is going to be there between the gas molecules, that is assumed to be negligible, or you can take it to be absent. Or you can, it's better to say the interatomic force is, or intermolecular force is negligible. Intermolecular force is taken negligible. Intermolecular force is taken to be negligible. It means there is no force of interaction between the molecules. Man, if that force is absent, there is no concept of potential energy. For example, you take me to be one gas molecule and earth to be one gas molecule. If there is no force of attraction between me and earth, will there be any gravitational potential energy? No. The concept of potential energy comes from these forces. So if these forces are absent, no potential energy is going to be existing. Then if I am going to talk about the total energy possessed by the gas, the total energy possessed by the gas is going to be generally the potential energy plus the kinetic energy. As I have taken the intermolecular forces to be negligible, there is no potential energy. So the only thing the gas is going to have, or the only way the gas is going to store energy, is only in the form of kinetic energy. The only way gas is going to store energy is in the form of kinetic energy. Now we have a problem, man. What is that problem? Let's see that. Yes. Look here. Is every gas molecule moving with same speed? No. Okay. For better thing, you look. Whatever the air we take, we will have lot of different molecules. Right? That's why different colors of the particles are different molecules. And you can see, even when I have taken these many number of gas molecules, the pressure is keep changing, right? That's why I was telling you clearly, man, make sure that you are going to take very huge number of gas molecules. Okay, fine. Look, all of them are moving in random directions, randomly with random speeds. You can see some of them are moving very slow, and after collision, all of a sudden they will start moving faster. Okay, let me decrease the molecule count so that you people will understand or see it better. You just look at this, even the color scaling also for simplicity. Okay, fine, I'll do the color scaling such that you people can feel. Look at this. This fellow is moving so fast, right? Moving in random directions. And this fellow is moving slow. This fellow is moving slow. So like that, different gas molecules are going to be moving with different speeds. And are they going to remain the same for a particular gas molecule? Is the speed going to always remain the same? No, that is also not possible, because every time when it makes a collision, its speed is going to be changing. Okay, fine. So, if I want to talk about the kinetic energy, we have a lot of molecules, man. So, if I want the total kinetic energy of all the gas molecules, for simplicity, what I am doing is I am taking a single gas, like all the gas molecules are same. Like one type of gas is what I am taking now. So, half m v1 square, half m v2 square, and so on. So this is what. Now look, I can take half and m common, then I am going to get v1 square plus v2 square and so on. What I will do is, I will multiply with total number of gas molecules and divide with total number of gas molecules. Now, the total gas molecules multiplied with mass of each gas molecule gives you the total mass of the gas. Small m is mass of each gas molecule, capital N is total number of gas molecules, small m into capital M gives you the total mass. So, half small m into capital M, and this is what, v1 square plus v2 square and so on, divided by capital N. Okay, what is this? Total mass. And what is this one? Mean of the squares or not? This is mean of the squares. Mean of the squares. Okay, and this is going to be the total mass of the gas. So now this thing I will represent with one letter called as VRMS square. And what is that VRMS square? Obviously VRMS square is this one, which is going to be V1 square plus V2 square and so on, divided by the capital N. And that VRMS, if I am going to talk about, is going to be under root of V1 square plus V2 square and so on, divided by capital N. Now you should understand why they have given the name as RMS. What is this? Root. This one is what? Mean of the squares. That's why when they were representing this, they have gone for a letter and they have gone for an expression called as VRMS, because this represents the root of mean of the squares. So whenever you are going to talk about kinetic energy, now you clearly know which speed you have to use. You have to use RMS velocity. And whenever you are going to talk about distance traveled by the gas molecule, you have to talk about the average speed. This is one such thing where majority of the students have problem. Majority of students have problem. So always keep this in mind. If you are talking about kinetic energies, you have to talk about RMS velocity. If you are talking about distance covered by the particle, you have to talk about average speed, right? What is E? Coefficient of restitution. The coefficient of restitution, collisions. Okay. Now look, the total energy, which is going to be the kinetic energy, which is going to be half capital M VRMS square. And for your kind information, the total energy only is going to be called as internal energy of the gas. internal energy, and in future we are going to represent it with the symbol U. And one more thing, this internal energy of the gas, which is nothing but total energy of the gas, is nothing but kinetic energy of the gas, is because of the random movement of the gas molecules, is because of the random movement of the gas molecules. Never ever forget that. Internal energy is because of the random movement of the gas molecules. Okay, fine. Next. What else? Look here. Look here. All these gas molecules, are they accumulating onto one side? Can you see that? Or all these gas molecules, after some time, are they accumulating at the top? Or all of them accumulating at the down? No, that's not happening. The reason is, if you look at all of them as an average, the average velocity, for example, let us say, if all the gas molecules have an average velocity in the I cap direction, if they have it in the I cap direction, after some time, this whole gas should have accumulated here, because they are preferring in I cap direction. If they have the average velocity in the J direction, all the gas molecules should have accumulated at the top. But is that happening? Can you see that? No. Sir, this is simulation, sir. It will be in our hands. Whatever the coding we do, based on that, it is going to show. How can you explain in reality? Man, for example, if the air in the room is having an average velocity in this direction, after some time, the air around me should have moved to that side and I should feel breathlessness because there is no air around me. But is that happening? No, it is not happening. No, it is not happening. Okay. I already explained it's that potential energy won't exist. You please rewind in the video. I have explained. You just go back and see. Okay, fine. So if I'm going to talk about the average velocity of all the gas molecules, pakka for sure, the average velocity should be 0. The average velocity should be 0. Okay, that logically I have explained. But will the average speed be 0? No, man. You have particles having some speed. So when you talk about average, speed is never going to be negative. As a result, average speed will be there. Okay. What else, sir? Is there any other assumption which we have to take into consideration? No. These many assumptions are enough for us to understand the whole kinetic theory of gases. For us to understand the whole kinetic theory of gases, this much is sufficient. Okay. The very first thing we are going to start with is going to be gas laws. Right? Now, if I am going to talk about Boyle's law, man, what is this? I think constant temperature. At constant temperature, for a given mass, at constant temperature, pressure into volume is constant. Okay, what will be the graph? Look, man. So this is one conceptual problem with majority of the students. Their brain is going to be processing the graphs when the equations are given in terms of x and y. If the equations are given in terms of something else, for example, PV is equal to constant or V into R is equal to constant, their brain won't process it. I don't know for what reason. That's a problem with everyone. So I am included in those everyone. I also have a problem. My brain doesn't process stuff faster. So as my brain is going to process x and y's faster, whatever will be plotted on y-axis, you write that as y. Whatever will be plotted as on the x-axis, you write that as x. Then you will get x and y relation. Then our brain is going to be processing the stuff faster. Look, this, you write it as y, this, you write it as x. and then it has become y into x is equal to constant. X into y is equal to constant is going to be a rectangular hyperbola. How it is going to look like? It's going to look like this. Now, as you already have information about temperature, for example, if I'm going to say, or if I'm going to draw a graph between P and T should not change. That means x coordinate should not change. Then it should be a graph parallel to the y-axis or not, because T shouldn't change. And then if I am going to talk about Vt, if I am going to talk about Vt, so for Vt also, what is going to happen, man? T is not going to be changing. So you should draw a line which is going to be parallel to the y-axis. Good evening, Manisha. Oh, now Charles law, pressure constant, and here, like, it's something which is going to be very important. Even the graphical analysis is going to be very important. Lot of times they have given that. I'll draw that and I'll show you that. Okay, Charles law. What is Charles law? For given mass of the gas, for given mass of gas at constant pressure, at constant pressure, volume is directly proportional to temperature. Man, this temperature should be put in terms of absolute temperature. That is going to be what? Kelvin. Only then volume can be said to be proportional to temperature. Otherwise, you can't say it. In that case, volume is going to be some constant into T. I am going to plot a graph between V and T, man. My brain doesn't process V and T good. My brain processes Y and X good. Whatever is plotted on y-axis, put it as y. Whatever is plotted on x-axis, put it as x. If I do that, what am I going to get? I get y is equal to some constant into x. So this is of form y is equal to mx. That means it should be a straight line passing through origin. So from next time onwards in questions, you will be given graphs like this. If they are going to give a graph passing through the origin, volume is proportional to temperature. If they give P and T, and if it is a straight line passing through origin, then pressure is directly proportional to temperature. If it is P and V and a straight line passing through origin, then pressure is proportional to volume. Keep that in mind. Okay, fine. Now, for the very same thing, if I am going to talk about a graph between P and T, for your kind information, pressure is constant, right? That means y should be constant. If y has to be constant, it should be a straight line parallel to the x-axis. It should be a straight line parallel to the x-axis. Next, if I am going to talk about, let us say, what is left? PT is done. Okay, PV. If I am going to talk about PV, here also I know that pressure has to be constant. And keep one more thing in mind. Pressure has to be put in terms of Pascal. Volume has to be put in terms of meter cube. T has to be put in terms of Kelvin. Never ever forget that. Okay, fine. Gay-Lussac's law. What is the Gay-Lussac's law? For a given mass, for a given mass of gas at constant volume, pressure is directly proportional to temperature. So pressure is going to be some constant into T. So if I am going to be plotting a graph between P and T, look, whatever is going to be there on y-axis, you keep it as y. Whatever is there on x-axis, you keep it as x. Then it is y is equal to cx. That means it's a straight line passing through origin. Next, if I am going to talk about V and T, what did they say? Volume is constant. Volume is constant. If I am going to talk about, PV, then volume is constant. That means it should be a straight line parallel to the y-axis in this case, because we should not change. Okay, we have to go through these gas laws as fast as possible. What is Avogadro's law? What is Avogadro's law? For a given temperature and pressure, equal volumes will have equal number of gas molecules. For a given pressure and temperature, equal volume of all gases will have equal number of molecules. Whether it might be nitrogen, hydrogen, you can say helium, no matter what you are talking about. Okay. Now Dalton's law of partial pressure. In a container, if we have more gases, not one, we don't have one type of gas, we have more. For example, helium is there, hydrogen is there, nitrogen is there, oxygen is there, carbon dioxide is there. So if we have a mixture of gases, total pressure is sum of the individual pressures due to all the gases. See, one thing which I have noticed is that JEE has touched almost everything. For example, constant pressure, constant volume, and all those things. But they haven't touched the Dalton's law of partial pressure much in physics. So there is possibility that in the coming future, they can touch the Dalton's law of partial pressure. That's why I have taken a question. But to solve that question, please, you should know ideal gas equation. So first I'll do, before solving this question, I'll just give you the ideal gas equation which has come from all those gas laws. We have seen 5 gas laws, right? When we put all those 5 gas laws together, we get one equation for ideal gas. What is it? PV is equal to nRT, where N is the number of moles, R is the universal gas constant, T is temperature, which should be put in Kelvin. T should be put in terms of Kelvin, right? P should be put in terms of Pascal, and volume should be put in terms of meter cube. There is one more thing which you people should know. See, P into V can be written as what? Total number of molecules by the Avogadro number gives you the number of moles multiplied with R into T. See, this R by Na is going to be called as Boltzmann's constant, right? Is going to be called as Boltzmann's constant, but this is the one which we are going to use very frequently, and sometimes we are going to talk about density, man. So you should know the ideal gas equation in terms of density also. So basically, P into V, number of moles can be written as mass by molar mass into RT. Now, P, I can take volume to this side, then M by V by M naught RT. M by V, mass by volume will be what? Density. So pressure is going to be rho RT by M naught. Is rho RT by M naught. This is the ideal gas equation which you people should know. How these things have come from those 5 gas laws which have been seen or observed experimentally. Okay, now you solve this question. I have to give you some info. Please take the molar mass of air to be 29 grams and the molar mass of nitrogen, please take it as 28 grams. That's the data which is given. As I said, there is high possibility of these kind of questions in near future, because this is one part which is not explored by NTA. not explored by NTA in the recent past. Okay. We know that air is made up of different gases. So the room where I am standing has oxygen, has nitrogen, has carbon dioxide, has everything, man. Has everything. Right? But I know that the atmospheric pressure is 1 atmosphere, or you can say 10, roughly 10 to the power 5 Pascal. Out of that 1 atmosphere, how much pressure is contributed by nitrogen? And you might have a doubt, sir, how the pressure is going to be there, sir? Look at this. Look at these things also. So when these gas molecules are going to go and collide with the walls of the container, when they go and collide with the walls of the container, their momentum is changing. Who is changing the momentum of the gas molecules? Walls of the container. That means walls of the container are applying force on the gas molecule. For every action, there will be equal and opposite reaction. Then gas molecules will apply force on the container. That force per unit area is going to be the pressure. Right? So now you understood how the pressure is going to be acting. You just tell me what will be the answer for this. The mass percentage in composition of dry air at sea level contains approximately 75.5% of N2. Right? If the total atmospheric pressure is 1 atm, then what will be the partial pressure of nitrogen? Okay, man. Look, we know the ideal gas equation. PV is going to be mass of air which is under observation by molar mass of air into RT is what I write. And this P is going to be 1 atm, 1 atmosphere, because we are talking about the whole air. So pressure by the total air. Okay, I'll write P air. Now, if I am going to talk about pressure contribution by nitrogen into volume is mass of the nitrogen by the molar mass of the nitrogen into RT. Man, you take this as equation 1, you take this as equation 2. So if I am going to talk about equation 1 divided by equation 2, what am I going to get? Pressure of air by pressure by nitrogen is going to come out to be what? If you observe carefully, mass of, okay, 1 second, 1 second. For better calculation, I'll do equation 2 by 1. Not by 1 by 2, I'll do equation 2 by 1. So when I'm going to talk about equation 2 by 1, pressure contributed by nitrogen by the total pressure of air is going to be mass of nitrogen by mass of air is going to come multiplied with molar mass of air by molar mass of nitrogen. Man, this is given, man. This is given. How much is it given? This one is given as 75.5%. That means this can be written as what? This part can be written as what? This part can be written as 75.5 divided by 100. What is the molar mass of air I asked you to take? 29. Molar mass of nitrogen? 28. So let me do the calculation. Let me do the calculation. 75.5 into 29 divided by 100 divided by 28, which is going to be 0.78. So the ratio is 0.78. What you do is you just take the pressure of air to that side. Pressure of air is 1 atm. So as a result, the pressure due to the nitrogen gas is going to turn out to be 0.78 atm. 0.78 atm. That's it. So this is one good question which you people should think, and this is a common question which you are going to find in good books, right? The approach is going to be a bit better here. Like what I have done, this approach or this way of thinking is going to give you better clarity. Ideal gas is also done. Now, using ideal gas, let us take some basic questions. See, during an experiment, an ideal gas is found to obey an additional rule. It means the moment you say ideal gas, PV is equal to nRT. Apart from that, it is also obeying Vp square is equal to constant. The gas is initially at temperature capital T and volume capital V. What will be the temperature of the gas when it expands to 2V? Man, see, they are talking about temperature and they are talking about volume. We don't need pressure. We have to get rid of it. So we need only VT relation. So what did they give? They have given that Vp square is equal to constant. As the relations are between T and V is what is asked from us. So we have to eliminate P. And we have PV is equal to nRT from ideal gas. So P can be written as what? nRT by V is going to be what? Constant. And there is a square here. Now look man, n is a constant, r is a constant. So n square, r square, and it is going to go on to this side. This constant by n square, r square will become some new constant. Let's say, for example, if this is 10 and if this is going to be some 2, then 10 divided by 2 will become 5. It's a new constant, but still it's a constant. So t square by v is going to be constant. Or if you want better conceptual clarity, please write it as some new constant. This constant and this constant are different. It's fine. Okay. Now, what will be the temperature of the gas when it expands to 2V? Look down. T1 square by V1 should be equal to T2 square by V2. T1 is taken as T. Volume V. T2 square. I don't know what is the temperature, but what is the volume? It is 2V. V and V gets cancelled out. So T2 square is 2T square. So what is T2? T2 is root 2 times T. That's it. That's it. Okay. Next. This is one good question. This is one good question. Why? Because you are talking about open container. When you talk about open container, some gas from atmosphere can come into the container or some gas might leave the container. Right? So this is a good question, and I feel that this is also one more model which can repeat, potentially good model. Temperature of an open room of volume 30 meter cube increases from 17 degrees to 27 degrees due to sunshine. The atmospheric pressure in the room remains to be 10 to the power 5 Pascal if Ni and Nf are the number of molecules in the room before and after heating. Number of molecules. Generally, when we talk about number of molecules, we represent it with capital N. Man, see, when I am going to talk about PV is equal to nRT, PV is the number of molecules by the Avogadro number into R into T. Right? Okay, fine. Now, how do I get this N value? The N value is going to be PV Avogadro number divided by RT, right? These are the number of molecules. So we have taken a container which is open, but the volume of the container is 30 meter cube. That is not going to change. So if the temperature changes, automatically you only can clearly see pressure is remaining as it is, volume of container is remaining as it is. As the temperature is going to increase, the number of molecules that are going to be present should definitely decrease. And what they are talking about, N final minus N initial. For your kind information, P, V, Na, R are same. So P, V, Na by R are same. Is 1 by T final minus 1 by T initial. T final 27 plus 273, which is going to be how much? 300. and this is going to be how much? 273 plus 17, which will be 290. So you put the values, man. So P is going to be how much? P is going to be 10 to the power 5. What is the volume? The volume is 30, and Avogadro number roughly 6 into 10 to the power 23 divided by the gas constant by 1 by gas constant, you can put 8.3. 1 by 300 minus 1 by 290, it's a clear indication that this is going to be negative. How many options have negative answer? 1, 2. These two are eliminated, and these are the only two things which have negative answer. As a result, if you do the calculation, you get option 3, which is minus 2.5 into 10 to the power 25. Okay, super. Now, if we talk about the speed distribution of the gas molecules, we have already seen, man. You remember? You can't pick any one gas molecule and talk about the exact speed of the gas molecule. It's a probability spread, Maxwell distribution of speeds. If you are going to talk about, let's say, velocity is 300 meters per second, how many gas molecules are going to have exactly 300 meters per second? No one can calculate that. What Maxwell gave, how many number of molecules are going to be having a speed between 300 to 300.000000001. So no one can exactly calculate what will be the, like, how many particles are going to be having this exact speed. So it's always going to be a spread. It's always going to be a spread. I think we don't have it in our syllabus, Maxwell distribution of speed. So I don't need to give that probability curve, whatever is going to be there. One big expression will be there. Not at all needed. All you need to know is that they move randomly. They move randomly, right? So using that probability distribution, as we know that in the container, whatever the gas molecules I take, they are going to be moving in random directions. When I talk about, let's say, for example, this to be some V1, this to be some V2, this to be some V3, this to be some V4, this to be some V5, this to be some V6, like that. Let us take some speeds. But as I said, in reality, no one is going to pick one gas molecule and talk about the exact speed of it. It's just distribution. So always keep in mind how many gas molecules have their speed between 300 to 300.0000001. Not exactly 300. Range is always going to be given. No, Balireddy, Govardhan, to get decent NITs, your percentile should definitely be close to at least 98. Like third tier NIT, some random shitty branch also, if you want, you need to have 98 minimum. If you belong to general category. Okay, fine. So when I'm going to talk about the RMS speed again, speed is root 3 RT by M naught. One very interesting thing is that it's only depending on what? Temperature. It's depending only on temperature. Keep that in mind. Okay. And then if I am going to talk about the average speed is root 8 RT by pi M naught. And what is m naught, man? M naught is molecule molar mass. Molar mass. I will be taking this class roughly around 2 hours or 2.5 hours. That's it. 2.5 hours. The most probable speed. What is most probable speed? That's the speed majority of the gas molecules are going to have. And this is the average. And this is the root mean square. How we got all these things? It is from the probability distribution curve of Maxwell. Okay. But man, if you want to talk about the internal energy, or for example, the translational kinetic energy. For example, if you want the total translational kinetic energy of the gas, you already know that the translational kinetic energy is going to be half capital M into V RMS square. In the beginning only I proved this. Half V RMS square is going to be what? 3 RT by M naught. And M by M naught can be written as what? Moles. So can we write it as 3 by 2 nRT, and this is what is going to be, okay, fine. Let us keep it like this. Don't call it as internal energy. I'll talk about why we shouldn't call that as internal energy. But majority of questions are coming from KTG from this part, or they are coming from mean free path. Majority of the times the questions are going to be from this gas molecules part or from mean free path. Okay, let us look at some of the questions. Try the questions. Try them. For a given gas at 1 atm pressure, RMS speed of the molecule is 300 meters per second. It's 200 meters per second at 127. At 127 degrees. At 2 atm pressure and at 227 degrees, the RMS speed of the molecules will be. Majority of the people are going to be looking at 2 atm and they are going to get confused. Why are they specially mentioning the pressure? Man, not needed. It's just an extra data trying to confuse you. So if they are going to talk about RMS speed is proportional to root T. That's it. RMS speed is proportional to root T. That's it. Let me pick this color, how it looks like. So the RMS speed at 127 degrees and the RMS speed in the second situation is going to be root T1 by T2. Root T1 is what? 273 plus 127, which is going to be how much? 400? Yes. Divided by the other is 227, which is going to be how much? 500. So we know that the RMS speed in the first case is how much? It's 200 divided by VRMS 2 is 2 by root 5. So the VRMS 2 is going to be how much? 100 root 5. 100 root 5. Okay. Next. Now, try doing this. I didn't understand Praveen Kumar Korada. When was your class stopped? I didn't get you, man. I didn't get you. A mixture of 2 moles of helium and 1 mole of argon is kept at 300 Kelvin in a container. The ratio of their RMS speeds, man, they have same temperature, right? See, if you are going to look at the RMS speed if you look at it, it is root 3 RT divided by M naught. 3 is constant, R is constant, capital T is constant. Why I said capital T is constant? They only said that in the question that the temperature is same. Okay. Then the RMS speed of helium to the RMS speed of AR, as the RMS speed is inversely proportional to the molar mass, you have to talk about molar mass of argon, which is going to be 40 grams divided by the molar mass of this, which is going to come out to be root 10. Root 10 is going to be roughly 3.14, or you can say it's going to be close to 3.16. Thank you, Sharif IIT. Where are you from, Mr. Sharif? Meanwhile, people do this. But as I said, from KTG, majority of the times, the questions are on this RMS part or the degrees of freedom part or mean free path. These are the general questions, and whenever it is mean free path, people are literally scared like hell. You don't worry, I am going to properly give you today, and I am going to give you the important things, like, or you can say the ones which you can mug up. Even if you don't understand what is happening, you can't visualize what is happening, still I am going to give you one formula. At room temperature, a diatomic gas is found to have an RMS speed of 1930. They are talking about the gas. And what are they talking about? At room temperature, right? I'm just taking that the room temperature is going to be around some 27 degrees or so that the calculation part is going to be easier. So VRMS is going to be root 3 RT by M naught. So the molar mass is going to be 3, some 8.3 into temperature. I am taking it to be 27 degrees Celsius, India, right? Take it to be some 27 plus 273, which is going to come out to be 300 divided by 1930 square, right? So when I do that, and one more thing, obviously the molar mass should come in terms of grams, right? Should come in terms of grams. So what I will do is, see, I'll write it as 9 into 8 to the power 8.3 into 100 by 19.3 into 19.3 into 10 to the power 4. So from here, I can say 9 into 8.3 by 1.93 into 19.3 into 10 to the power minus 3 kg. So this is what we are going to put it as grams. Now from here, you can clearly see that, see, if I am going to talk about F2, O2, Cl2, they are way big in mass when compared with H2. Look at this. This is around what? This is 8.3 into 9, which is going to be roughly 72. 72 divided by roughly how much? 38. So it is roughly in the order of 2 grams, right? Who is going to have 2 grams? Obviously hydrogen. Look, they are very good, man. I love the person whoever has framed the options. Why? If they have given hydrogen and in the other options helium, I couldn't have done the rough calculation. Because helium is going to have 4 grams and hydrogen is going to have 2 grams, but they have given the other things to be too big, and you are definitely not getting a too big one. So if I use calculator, 9 into 8.3 divided by 1.93 and divided by 19.3, which will give you roughly 2. So 2 grams is going to be for hydrogen. It's going to be starting, it's JEE, it's going to be starting from first week of December. Okay, this is also a good question. From this also you are going to learn something new. A gas molecule of mass capital M at the surface of Earth has kinetic energy equivalent to 0 degrees Celsius. That means it is 273 Kelvin. It is 273 Kelvin. Okay, gas molecule of mass capital M. Man, look, when I am going to talk about kinetic energy, we should talk about the RMS speed, which is going to be root 3 RT by M naught. But here M naught is molar mass, but they are talking about gas molecule. That means I have to go for molecule. If I have to go for molecule, 3 RT in 1 mole, we have Avogadro number multiplied with mass of each molecule. R by Na is going to become what? Boltzmann's constant. So it is going to be 3 kT by M. So now, if I am going to talk about V RMS square, it is going to be 3 kT by capital M. Just keep this in mind. So the gas molecule has this much speed square. It is going to go up with that speed. And they clearly mentioned that assume that the height attained is much less than the radius of Earth, indicating throughout its upward journey, more or less the acceleration due to gravity is constant. Just like when I throw my pen up, when I throw the pen up, what is going to happen? As it is traveling lesser heights, more or less you can take the acceleration due to gravity to be 9.8 or you can mention it to be g. So they are asking about how high it would rise. So when it is going to be at the topmost point, the maximum height it is going to reach is when it is going to come to rest. So v square minus u square is equal to 2as can be used. V square minus u square is equal to 2as formula can be used. Final velocity 0. Initial velocity square 3 kt by m is going to be 2 times minus g. I am taking up as positive while using this formula. So from here h is going to come out to be what? 3 kt divided by 2 mg or not? 3 kt divided by 2 mg and t should be 273. 273 into 3 is going to give you 819. So which option? It's option 1. 3 kt by 2 mg. So these kind of questions when they are going to be asked, the people are going to be first of all scared. Hey, come on, what is happening? They have converted it into a simple projectile motion. Ultimately what happened? The gas molecule is going or projected vertically up. That's it. It's projected vertically up. So when you are going to be reading the question, keep your emotions aside, be mechanical, just write down the data and then try to connect all those data points. Half of the questions in physics are going to be done in that way. But first, as I said, mentally, psychologically, you have to keep that aside. Emotions, you have to keep it aside. Okay. Then, pressure of the gas on the walls of the container. Pressure of the gas on the walls of the container. Look, let me pick one gas molecule, a monoatomic one. It has some velocity Vx1 in this direction, some velocity Vy1 in this direction, and some velocity Vg1 in this direction. Now, once it makes collision, once this is going to go and collide, I already explained in the beginning of the lecture itself, its velocity gets reversed along the line of impact, but the other velocities whatever are there they will remain as it is. They will remain as it is. For example, see, if the particle is coming and pressing like this, that's when there will be force. But if the particle is sliding like this, or if the particle is sliding like this, will there be any force? No, there will not be any force. Okay. Now, let us talk about change in momentum. Let us talk about change in momentum of the particle. What is the initial momentum of the particle? Small m, mass of the molecule. Small m, mass of the molecule. Small m is mass of the molecule into Vx1 I cap. What is the final momentum of the gas molecule? Small m into Vx2, sorry, Vx1 only. Vx1 minus I cap. So what will be the change in momentum? Obviously, it is going to be the final momentum minus the initial momentum. Final, it is in this direction. Initial, it is in this direction. So final is going to come out to be what? Minus mvx1 I cap minus, what is the initial? mvx1 I cap. As a result, the total change in momentum is going to be 2mx1 I cap minus. Right? Okay, fine, good. What that particle does, man? What that particle is going to do? After colliding with this wall, it travels. Let us take this to be a cube of side L. Let us take this to be a cube of side L. Now, after colliding, it travels L distance, again collides with this, again travels L distance. So, to again apply force on this or to collide on this wall again, how much distance it has to travel? It should go L and it should go L in this direction. So, the total length it has to travel is 2L. And with how much speed it is traveling? Vx1. So, what is the time gap? What is the time gap between successive collisions? It has to travel 2L distance and it is traveling with a speed of Vx1. In this much time gap, it is going to go collide and come back. Now look, if I am going to talk about averagely, how much force is applied on the wall of the container? We have this change in momentum happening for every how much amount of time? This much amount of time. So the average force on the gas molecule is going to be the change in momentum divided by the time. What is the change in momentum? Minus 2mvx1 I cap by what is the time? 2L by Vx1. So what are we going to get? The average force is minus mvx1 square divided by L. Is this you get? And this is the force on one gas molecule by the wall. We have action reaction. We have action reaction. On the gas molecule, if this is the average force, on the wall, force, or you can say average force on the wall by each molecule is obviously mvx1 square divided by L. mvx1 square divided by L I cap. Action in minus I cap direction. Reaction is in plus I cap direction. Sri Vignesh can't help. If you want Shreyas sir to be taking, right? In this chat, no one is going to see. I will be seeing it. I am the one who is going to look at it. And obviously my flow is going to get broken, right? So there is no point in writing over here. There will be some email IDs or whatever, or he is teaching in that need channel. You can go and follow over there. I can't help. There is no point you coming and texting here. And I won't feel bad at all for your kind information. This is my background. I don't feel bad. It might be my frequency is not setting with you. That's it. So might be you understand better from different teacher. That's perfectly fine. But texting here won't help. Won't help. It's just going to break my flow. Nothing else. Nothing else. So spamming is not going to help. Spamming is not going to help. Okay. Average force on wall by each molecule, we got this. But do we have one molecule, man? Look at this. We have so many, right? We have so many of them which are going to be colliding with the walls. And are all of them going to collide with Vx1 speed only? No, they can collide with any speed. So there is no such guarantee. There is no such guarantee. No, Vishal, see, it's not about best reply and all those things. See, I'm a strong believer. According to me, every teacher is good. Only thing is that if their frequency and your frequency is going to match, we say right in physics, resonance, extremes are going to happen. The amplitude of oscillations are going to become maximum. So that's when you get maximum knowledge. That's when you get maximum knowledge. That's what I believe in. Ultimately, you people should get benefited. That's all I want. Because I am someone who is way beyond all these things. I'm way beyond all these things. I have already proved myself. There is nothing for me to prove anywhere. Okay, fine. Now, average force on wall by all the molecules, if you want, by all the molecules, if you want, we won't have one single, right? So MVX1 is due to first one. In the same way, we will have MVX2, the second one, and so on. So many particles are going to be there, right? Now, if I want, you can clearly see that it is going to be mean of the velocities only in the x direction. This is the force on the wall. Mean of the velocities in the x direction. And one more thing, on an average, the gas doesn't prefer x direction, y direction or z direction. It will have equal contribution. It will have equal contribution in all three directions. Keep that in mind. It will have equal contribution in all three directions. What I am trying to tell you is that if I am going to talk about VRMS square, you are going to have Vx square, Vy square and Vg square. The average or the RMS value in x direction, RMS value in y direction, and all three of them are going to be equal. So you can say Vx square, as I said, the gas doesn't prefer alone x, alone y or alone z. It will equally like all three directions. There is no bias. Okay. Then I can write it to be VRMS square divided by 3. But keep in mind, all these are also RMS values. So how do I get RMS values, man? From here, simply by multiplying capital N and dividing capital N. So I can say M by L into N into, I can say Vx square RMS. Right? Now you tell me what will come out to be the force on the wall. The force on the wall is going to come out to be Mn m n, that Vx RMS square can be written as what? V RMS square divided by 3 divided by L. This is the force. But we need pressure. We need pressure. I didn't understand it. Vishal, notes will be shared in the jungle book of this. Under the video, there is a description. In that, notes will be shared. Okay, this blue is not visible, right? From next time, I won't write this blue color. Okay, fine. Now look, we need pressure. We need the pressure. So pressure is going to be what? Force by the area. And for your kind information, I have taken this to be a cube. So what will be the area of this face? What will be the area of this face? It's going to be L square. It's going to be L square. As a result, if you are going to talk about, I'll take 1 by 3 m n V RMS square by L cube you are going to get, because L is already there and you are dividing with area which is L square. L into L square will become L cube. L cube is what? Volume. So the pressure is 1 by 3 small m into n into V RMS square divided by volume, capital V. And what is small m into n? Small m is mass of gas molecule. Capital N is the number of gas molecules. So mass of each gas molecule multiplied with the total number of gas molecules gives you the total mass. So pressure into volume is 1 by 3 capital M V RMS square. For your kind information, if it is an ideal gas, PV can be written as what? nRT, and N can be written as what? M by M naught into R into T, which is 1 by 3 M V RMS square. So the theory is suggesting that the RMS speed should be root 3 RT by M naught. Theory is suggesting that RMS speed should be this. This is a theoretical derivation. And experimental distribution by Maxwell. Maxwell gave a distribution of speeds. So from the distribution of speeds, when we calculate the RMS value, it came out to be this. So whatever the theoretical answer we have got and whatever has come from the Maxwell distribution, both of them are same. Both of them are same. Okay, fine. I did the complete derivation of this. In a flow, I have done the complete derivation of this one. Okay, now everyone understood how that force is being experienced. How that force is being experienced. Now, if I am going to talk about a monoatomic gas, we will have a single atom. And that monoatomic gas is only going to have translational kinetic energy. We will talk about that, but RMS speed is done. Let me talk about monoatomic. So if I am going to talk about a monoatomic one, we will have a single atom, and this single atom will have only translational kinetic energy, has only translational kinetic energy. Why it can't have rotational kinetic energy? Because we have taken the gas molecules to be occupying no volume. That means almost they are point masses. For you to understand, I have drawn them to be bigger, but in reality they are very small. So they can't rotate because they don't have moment of inertia. Okay, now they have only translation kinetic energy, which is going to be half mass of the gas into V RMS square. When I am going to do that, I will get it to be 3 by 2 nRT. When I substitute the VRMS value from here, I'll get 3 by 2 nRT. So this is the internal energy. This is the internal energy of n moles of monoatomic gas. Monoatomic gas. But if you want the internal energy of each molecule, then it will turn out to be 3 by 2 kT, which is going to be, K is going to be Boltzmann's constant. K is going to be Boltzmann's constant. You can easily get from here to here. First you get for 1 mole. In 1 mole you will have Avogadro number. From there you calculate for each member or each gas molecule. Each gas molecule. Okay, fine. Now look. Is it mandatory that we should have only monoatomic gas? Don't we have diatomic? Don't we have polyatomic? So we have different types of gases, right? It's not mandatory that we only deal with monoatomic ones. Okay, fine. So in order to dig deep in concepts, we need to understand something called as degrees of freedom. In order to dig deep in concepts, we need to understand something called as degrees of freedom. What is degrees of freedom? And whatever I'm going to give, please make sure that you are going to write a proper notes of it. No book is going to explain you in a clear way. No book is going to give you proper explanation. So please be careful. Write it neatly, properly. So what is degrees of freedom? Number of independent ways a body can store energy. Number of independent ways a body can store energy. Okay, definition is so good. Then let us go and deal with monoatomic gas. If I am going to talk about monoatomic gas, it's a single atom, man. It's a single atom. So this single atom can move in the x direction, can move in the y direction, can move in the z direction. Now look, can it store translational kinetic energy? Means, man, the translational kinetic energy formula is half mv square. So if the molecule has mass and if it is going to have velocity in x direction, definitely it is going to store. So it can store energy in x direction, translational kinetic energy in y direction and in z direction. So due to translation, in how many independent ways it can store energy? It can store energy along x-axis, y-axis and z-axis. Okay, fine. Let us talk about rotation now. See, when I'm going to talk about rotation, man, if you people remember, the rotational kinetic energy is going to be half I omega square, and this moment of inertia is going to be mr square, where r is the distance of the mass from the axis of rotation. Now look, let me take x-axis. As the mass is present on the axis itself, how much moment of inertia will be there? R is going to be 0. So the moment of inertia in the x direction is going to be what? 0. That means it can't store kinetic energy along this axis. Can it store kinetic energy along this axis? No. Can it store kinetic energy along the z axis? No. So it can't store any rotational kinetic energy, man. So the number of independent ways it can store energy in rotation, it's 0. It can't store energy. Only translation it can store. So 3 plus 0, total how many? 3. So the total degrees of freedom for monoatomic gas is 3. So total degrees of freedom are what? 3 plus 0, which is going to be what? 3. Which is going to be 3. Okay, now let us talk about, this is where things are going to become good. Books and me are going to differ in the sense, I won't say whatever is given in the book is going to be wrong. I am going to give additional data which is needed for JEE mains as well as JEE advanced. That is going to be diatomic. When I am going to talk about diatomic molecule, that means there will be two atoms. That means there will be two atoms. Okay, let me write that. Two atoms and they have a bond between them. So these two, they can move along x-axis, they can move along y-axis, they can move along z-axis. So what will be the kinetic energy, or it can store kinetic energy along, translational kinetic energy along x-axis, y-axis and z-axis. So from translation, how many ways it can store energy? In 3 ways. Now let us go for rotation. When we go for rotation, let me mark it. Right? So let me take an axis. This is your x-axis. This is our y-axis. And this is our z-axis. If I am going to talk about this axis, as both the masses are lying on the x-axis, both of them are going to contribute for zero moment of inertia. So Ix is going to be 0. So there can't be any rotational energy stored along x-axis. Right? Now look, when I am going to talk about this axis, we have a mass here, we have a mass here. And from this axis, this mass is at certain distance. Let me show you that. You can see that there is some distance. You can see that there is some distance here also. So from this axis, as this mass is at some distance, there will be moment of inertia about y-axis and there will be moment of inertia about z-axis also. Right? So moment of inertia is present along Iy. So Ig also not equal to 0. So it can store energy along z-axis. So from rotation, we have 2. This is when things are going to become good. I didn't understand, Mr. Vishal. Why, sir, only in X, Y, Z plane? Man, X, Y and Z are something which I am choosing. I can take wherever I want. But keep one thing in mind. If a body is free to rotate, it will always choose an axis which is going to be passing through the center of mass. So definitely whatever the X, Y, Z you are going to take should pass through the center of mass. Now look, there is no need for me to mention that this is X axis. I could have taken this as Y. Then the rest of the two are going to be X and Z. You can take in whatever the way you want. But keep in mind the axis of rotation should definitely pass through the center of mass. Now look everyone. Let me just talk about vibration. Vibration is simply can be visualized like this. For example, if you have two blocks connected to a spring, if you compress them and leave, they are going to be oscillating, right? And they are also going to be called as vibrations. Those things are also going to be called as vibrations. If you compress these two blocks and leave, then they are going to be vibrating like this. So when there is a vibration, so each vibrational mode, what is this vibrational mode? The way they are vibrating. For example, they are vibrating like this, right? This is called as one vibrational mode. You get better clarity on vibrational mode when I am going to talk about polyatomic. Just wait. I'll come there. Each vibrational mode definitely has some potential energy stored between them and some kinetic energy. some potential energy stored, and there is some kinetic energy stored. So each vibrational mode has 2 degrees of freedom. 2 degrees of freedom. Keep that in mind. One is going to be potential energy, one is going to be kinetic energy. No, try to go back in the video and try to understand. It's not difficult, man. It is not difficult. What you didn't understand, let me know. I'll redo it if you want. But tell me what you didn't understand. I'll redo it if needed. So first of all, why these vibrations are going to come into picture, man? At very high temperature, na, look, this atom and this atom, they are connected by a bond, right? They are connected by some bond. Okay, let us take the marker to be the bond. At very high temperature, this bond length keeps changing. Sometimes it is going to go like this, sometimes it is going to go like this, go like this. They are going to be vibrating just like what? Just like the spring and blocks. Okay, rotation. Man, you take this to be the axis, and on that axis itself you have 2 masses. If the mass is going to be present on the axis, what is the distance of the mass from the axis? Isn't it 0? If this is the axis, if I keep one mass here, if I keep the mass here, what is the distance of the mass from the axis? It's 0. And what is moment of inertia formula? mr square, where r is distance of the mass from the axis. So r is 0, na? And as I said, definitely there will be only 3 axes possible, which are going to be like 3 mutually perpendicular. Why mutually perpendicular? Why we have to take x, y and z? Because x is independent of y and z, y is independent of x and z, z is independent of x and y. And we are talking about independent ways of storing energy. X axis, y axis and z axis, all 3 of them are independent of each other. That's why. Why we are choosing only x, y and z? Because x, y and z are independent of each other and we want independent ways of storing energy. That's why I'm choosing x, y and z. Okay, I hope you understood. So when you take this axis, no moment of inertia. And one more line, which is going to be along y-axis, should pass through the center of mass. Then automatically this mass has some distance, this mass has some distance. So yes, moment of inertia is present, mr square. And if you take z-axis also is passing through the center of mass. To the g-axis also, this mass is at some distance, this mass is at some distance. That means moment of inertia is not equal to 0, something is present. If moment of inertia is there, it can store rotational energy. So it can store energy along y-axis, it can store energy along z-axis. Now I think you understood why it is 2. There is moment of inertia along y-axis, there is moment of inertia along z-axis. That's why it can store along 2 axes. Okay, now look. At high temperatures, vibrations also takes place. At high temperature, vibrations also takes place. Deva Darsha is asking, sir, what if the axis is going to pass through this? First of all, the axis should not pass through any one of them. As I said, a particle or a molecule which is free to choose its axis will be rotating about its center of mass. Even if it is going to be passing through any one of the mass, the other mass will contribute for moment of inertia. This will not contribute, but this one will contribute. So moment of inertia is present. Now, for example, if you take that the z-axis is passing through this mass, but this mass will contribute for moment of inertia. Now that means moment of inertia is not 0. Okay. At high temperature, vibrations also takes place. So, if I am going to talk about diatomic one, at normal temperature, how many degrees of freedom? At normal temperature, the degrees of freedom are 3 plus 2. Translation, it can store 3. Rotation, it can store 2. But at high temperature, translation 2, rotation 2, and vibration also 2. Sir, how do we know that they are talking about vibration? There is one more way they are going to talk about it. When they say non-rigid, when they are going to use the terminology in the question non-rigid, then the number of degrees of freedom have to be taken 7, or better, let me write like this, should be taken 3 plus 2 plus 2. So if they are going to use the word rigid, that means the atoms are rigidly fixed. That means they can vibrate. When they use the word, we are talking about a rigid diatomic molecule, then those atoms are rigidly fixed, they can't move. If they say non-rigid, then the bond length can change. That means they can vibrate. That's what they are trying to indicate when they are going to use the word non-rigid. Okay, fine, super. Diatomic is done. Now let us go for polyatomic. And in polyatomic, I'll just talk about polyatomic linear. Man, same story, da. Same story. Translation, same story. For you to understand, let me just take some 3 atoms. See, all these 3 atoms, they have their bonds, right? This whole thing can move in the x direction, can move in the y direction, can move in the z direction. So the degrees of freedom due to translation, are going to be how many? 3. Now, if we are going to talk about rotation, right, we can take one axis which is going to be along the x-axis, as all 3 masses are present on that axis. No moment of inertia will be contributed. So moment of inertia in the x direction is going to be 0. That means there can't be any energy stored along this axis. Now about y-axis, moment of inertia is not equal to 0, it can store. About the z-axis, moment of inertia is not equal to 0, it can store. So the rotational part is how many? Only 2. It can store along y-axis, it can store along z-axis. Rotation can take place along these two. Now the problem with vibration at high temperatures. At high temperature, number of vibrational modes is going to be 3n minus 5, where n is number of atoms. So number of degrees of freedom, as I said, these are the things which you won't find in the books. Each vibrational mode will have some potential energy stored with it and kinetic energy stored with it. So the number of degrees of freedom for vibrational mode are 3n minus 5, like 2 times 3n minus 5. Now you might have it up, sir, what is this vibrational mode, sir? I will take an example of CO2 for you to understand. Is CO2 linear? Yes. Look, man, what are the different types of vibrations that are possible? Different types of vibrations that are possible. Look, C will be at rest. Oxygen and oxygen are going to be moving. That is, look everyone, C will stay where it is, right? Oxygen will be oscillating like this. This is one way of vibration. One way of vibration. C will stay where it is and O is going to be oscillating like this, right? One more way of oscillation. We have oxygen, we have C, and we have O. One more mode of vibration which was observed in nature was that these two are going in one way and C was vibrating in the other way. So vibrational modes are nothing but different ways the molecule can vibrate, different ways or different types of vibrations the molecule can have. That's what is meant by vibration mode. So this is one way. C will be at rest and these two will be oscillating like this. Here, these two are going in this way and C is going in this way. Later, these two will go in this way, C will go in this way. That is one way of vibration. Like that, two more ways are there. Two more ways are there. This is going to go like this, these things are going to go like this. Like that, different ways of vibrations. As I said, you people can't memorize for every molecule. Na? That's why I simplified it. The number of vibration modes it is going to have is 3n minus 5. CO2 has 3 atoms. So 3 into 3, which is 9. 9 minus 5, 4. That means 4 different vibrations it can have. It can vibrate in 4 different ways. Hope everyone understood the vibration modes. No book has given all this in this detailed clarity, man. So if you love the level of what we call the content that is being given to you, please press the like button. That's it. That's all we demand. The fee you people are going to pay to us is going to be some good comments and a like button. Okay, fine. So if you talk about the total degrees of freedom, it is 3 plus 2 plus 0 where at normal temperatures. At normal temperature. At normal temperature. At high temperature. At high temperature, the degrees of freedom are 3 plus 2 plus 2 into 3n minus 5. Those many degrees of freedom. I'll do that. Don't worry. Now, I'll do that, man. Don't worry. Polyatomic non-linear. Polyatomic non-linear. So for you to understand, what I'll do is I'll just take 3 of them which are not in the same line. They are connected like this. See, this whole setup can accelerate in x direction, can accelerate in or can have velocity in y direction, can have velocity in z direction. Man, translation is always 3. Translation is always 3. Now, if you look at the rotation part, now even x is going to contribute. Why? See, even if you are going to take the x-axis to be passing through these two, the third mass will contribute. Na? So, Ix is not equal to 0. That means it can store energy in this way. Iz is not equal to 0. It can store. Iy not equal to 0. It can store. So, normally, how many rotational degrees of freedom you are going to have? Here 3 for a polyatomic non-linear one. Right? Now look, high temperatures. When we talk about high temperatures, so these non-linear ones will have how many different vibrational modes? The number of different vibrational modes. Number of vibrational modes. The number of different vibrational modes they can have is 3n minus 6. Each vibrational mode will have potential energy stored and the kinetic energy stored. So the number of degrees of freedom number of degrees of freedom will be what? 2 times 3n minus 6. So now you tell me what will be the total 3 plus 3 plus this one. So I'll put a chart. I'll just put a chart. Look. Look everyone, and in fact I'm going to give you one more extra thing for your conceptual clarity. Look, when I'm going to talk about monoatomic, look, low temperatures. Low temperature I will be giving you, and normal temperatures, and for high temperatures also I'll give you. All of them here at one single place. See, at low temperatures, even rotational way, it won't store energy. Even if it is diatomic, polyatomic, and all those things also, only translational energy is observed. They won't store any energy in rotation. So at very low temperatures, only translational will be present. At normal temperatures, translational rotation will be present. At high temperatures, translational rotational vibration will be present. Right? So when I talk about monoatomic, 3 degrees of freedom due to translation, 0 due to rotation, 0 due to vibration. At normal temperature, 3 due to translation, 0 due to rotation, 0 due to vibration. At high temperature, 3, 0, 0. Now I'll talk about diatomic. When I talk about diatomic, at low temperature, only translation. That's the beauty. At low temperatures, the rotational energy is not getting stored in the molecules. When you talk about normal room temperatures and all those things, like 200 Kelvin, 250 Kelvin, at those temperatures, it is storing energy in the form of rotation also. At very high, it is this vibration. Now, polyatomic, but we are talking about linear. 3, 0, 0, 3, 2, 0, 3, 2, 2 times 3n minus 5. Now, polyatomic, non-linear. At low temperatures, only translation will be present. At high normal temperatures, translation as well as rotation will be present. At very high temperature, translation, rotation plus vibration also is present. This is the thing. That's it. Khatam. No book has given this table. Mark my words. No book has given this table. Clear everyone? Clear everyone? Is everyone clear? Please respond. Thank you. Okay. Only 2 people have responded. Might be others are writing the notes. Might be others are writing the notes. Now, for monoatomic, we got the internal energy to be how much? 3 by 2 kT. Monoatomic molecule or monoatomic particle, whatever is there, has got 3 by 2 kT amount of internal energy associated with it. Then Maxwell was like, man, what are the gas molecule is there? If it has some 5 different ways of storing energy, why it will prefer only one particular way? It should equally prefer all 5 different ways of storing energy. So then he came up with this law of equipartition of energy. What is that? Each degree of freedom has half kT energy stored. So if you talk about a molecule, each degree of freedom it is going to store half kT. So now look, if I want the internal energy of monoatomic molecule, I'm talking about molecule, then how many degrees of freedom? 3 into half kT, which is going to be what? 3 by 2 kT. This is for molecule, each molecule. If you want for 1 mole, so if you want for 1 mole, obviously, how many are going to be present in 1 mole? Avogadro number. So Na times each energy, like energy of each molecule. So Avogadro number into Boltzmann's constant will be what? 3 by 2 RT. If it is N moles, then 3 by 2 nRT. Yes, gag తెలుగులో కూడా చెప్తా. తెలుగు జేఈ వేదాంత తెలుగు జేఈలో చెప్తా. Okay, fine. Now look. What about diatomic, sir? When I am going to talk about diatomic, what is that? It is going to be 5 half kT. I am talking about normal, under normal temperatures. If it is going to be high temperature, then how many degrees of freedom? 7 degrees of freedom. 7 into half kT, 7 by 2 kT. Okay, fine. So if I want 1 mole of diatomic, then 1 mole of diatomic is going to be what? Obviously 5 by 2 kT multiplied with the Avogadro number, which is going to be what? 5 by 2 RT. Man, in the next class when I'm going to do thermodynamics, I'm going to prove all these things, like CV is going to be 3R by 2, CV is going to be 5R by 2 for diatomic. I'm going to prove them. Okay, fine. Ayyo, sorry. Now, if I am going to simply say polyatomic, if I simply use the word polyatomic, but if I don't mention whether it is linear or non-linear, by default take it to be non-linear. So we have 6 half kTs, which is going to be coming out to be 6 by 2 kT. So if you want 1 mole of the polyatomic one, is going to be having Avogadro number multiplied with 6 by 2 kT, which will result in 6 by 2 RT. That's it. No, I'm going to give a breakdown. Even my tongue is twisting. After this, before I do mean free part, before I do mean free path, this is the last question. After this, I'll give you some 10 minutes of break. From 2:30, I'm continuously teaching, so my brain also got saturated. Right? I also need some break. My tongue is twisting. The gas mixture consists of 3 moles of oxygen and 5 moles of argon. Look, man, when they use the word or when they say oxygen, we know that it is diatomic. Argon is going to be what? Monoatomic. At temperature T, considering only translational and rotational modes. I love this person. He is clearly mentioning that neglect the vibrational modes. Neglect the vibrational modes. Okay, the total internal energy of the system is what they have asked. So what is the solution? 3 moles of oxygen. So if you want the total internal energy, it is the internal energy due to oxygen and it is the internal energy due to argon. What is the internal energy due to oxygen? We have 3 moles. We have 3 moles of oxygen as it is diatomic. So it is 5 by 2 RT. Each mole is going to have 5 by 2 RT. And argon is monoatomic and it has 5 moles and each mole has 3 by 2 RT. So when we do that 15 and 15, so you are going to have 15 RT. So what is the answer? Answer is 3. Answer is 3. Okay? Clear everyone? Now look, break of 10 minutes. Break of 10 minutes. We'll be back. We'll be back at 8:07 p.m. And after I am going to be coming back, roughly you will have some half an hour of class. Roughly you will have some half an hour of class and it is a very logical section. This mean free path is going to be a very logical thingy, right? So I'll see whether I have to derive or I'll just give the expression, whatever it is. Whatever it is, you people comment based on that in the live chat. If you want derivation, I'll give derivation, or in fact, if you want me to just do what we call the important section, whatever is needed, I'll just give you that also, right? Important section is more than enough rather than derivation. So let's see. Okay, I'll come back 8:07. Okay, I'm back. Look, so the next part we are going to deal is going to be mean free path. The next thing we are going to do is mean free path. So what is this mean free path? The average distance, the average distance, average distance traveled by gas molecule between two successive collisions, between two successive collisions. The next class tomorrow, it is going to be on thermodynamics. Okay, we will be doing thermodynamics. Now you see over here, if we are going to look at the particles, see, each particle is traveling different amount of times between two successive collisions. Each particle. That's why we are going to talk about averagely. And second, if you pick one particular particle, sometimes it travels very large distance before making a collision. Sometimes immediately it makes a collision. So even if you choose a single particle, it will not always have a constant distance traveling between two successive collisions. For example, let us pick this particle. Look, collided, right? Traveling. Now collided. It came this side. It traveled lot of distance without making collision. Lot of distance, collided. Lot of distance, collided. Look at it. Traveling a lot of distance, collided immediately. Some 3 collisions have happened immediately. So, if you pick even one single gas molecule also, sometimes it travels large distance without colliding. Sometimes it travels very small amount of distance between two successive collisions. Like that, the distance traveled between two successive collisions is random. It's continuously changing. That's why we talk about averagely how much it has traveled. Averagely how much it has traveled, and that average distance the gas molecule travels between two successive collisions is called as mean free path, and it is represented with the symbol lambda, right? It is represented with the symbol lambda, and that value is root 2 n pi d square. What is this? What is n? Number of molecules present per unit volume. Number of gas molecules. And then if you are going to talk about small d, it is diameter of the gas molecule. So this much distance, averagely the gas molecule is going to travel this much distance without making a collision. This much distance. Those who want to see how the particles are going to be moving, they are going to be moving like this. Here you have a lot of particles moving, right? You can see randomly in all the directions now. And they are going to be traveling different distances between two successive collisions. That's why I am talking about average, right? So if I am going to talk about what is the average time between two successive collisions, average time between two successive collisions, average time between two successive collisions is called mean free time is called mean free time, also called as sometimes relaxation time. So that relaxation time or whatever is going to be represented with the symbol tau. So how do we get the tau? Man, we know one thing, distance traveled is going to be what? Speed multiplied with time. So if you want time, then it is going to be what? Distance divided by the speed, right? Now, if you want the mean free time or the average time between two successive collisions, is the average distance it is going to be traveling by the average speed, right? Sometimes they are going to talk about frequency of collisions. Sometimes they are going to talk about frequency of collisions. So when they are going to talk about frequency of collisions, frequency is going to be 1 by time period, which is nothing but 1 by the time gap between two successive collisions. So you can say V average by lambda. V average by lambda is going to be the frequency of collisions. So these are the three different types of questions they are going to ask. These are the three different types of questions they are going to ask. Yes, Mr. Vishal, are you talking about English crash course? There is an English crash course which is launched. There is a Telugu crash course which is launched, but I will not be teaching in any of them. Okay. But the teachers, whoever are going to teach over there also are experts. In their own regions, they are experts. All of them are good. Okay, done. Now look, these are direct formulas. These are direct formulas. These are direct formulas. Majority of the times you will have questions directly on the formulas. But sometimes they are going to talk about temperature and pressure. They will be talking about temperature and pressure. So in that case, how we have to solve the questions? Let me just look at the mean free path. It is 1 by under root of, actually we should write it as what? Small n pi d square. So now that small n can be written as what? Root 2 total number of molecules by volume into pi d square. Right? Now, if I am going to talk about that PV is equal to nRT thingy, n by Avogadro number into R into T, then from here n by V is going to be P times Na by RT or not. So if I am going to put it over here, then for a particular gas, when I say for a particular gas, diameter of the gas molecules will be constant. Pi is anyway constant. Gas constant is a constant. Avogadro number is a constant. So in that case, can I say that it is inversely proportional to P by T, or if you write it properly, the mean free path will be directly proportional to temperature by the pressure. This is what I expect you people to memorize along with the mean free path. Along with this formula, I request you people to memorize this also. Happy birthday, Rangasamy. Jaya Murugan, I think it is not possible, man. I think it is not possible. You can't switch from English to Tamil. I don't think it is possible, although I'll just ask them and I'll see if that is going to be possible or not. Okay. Now they will be asking questions on relaxation time also. See, relaxation time or the mean free time is going to be lambda by V average. Man, lambda is proportional to T by P and V average is proportional to, okay. So if I'm going to talk about lambda, it is 1 by under root of n pi d square, and V average is going to be root 8 RT by m naught. Who is going to memorize this big expression, man? Look, the relaxation time or the mean free time is going to be directly proportional to, look, lambda is going to be T by P and V average is going to be proportional to root T. So the relaxation time is proportional to root T by P. And if they are going to talk about the frequency of collisions, then the frequency of collision is going to be 1 by time, right? So the frequency of collision will be proportional to P by root T. So these are the expressions. So whenever they are going to talk about frequency of collisions or mean free time, or they are going to talk about mean free path, these three things are going to be useful if they are talking about the very same gas, but they are making changes in pressure and temperature. If they are making changes in pressure and temperature, then yes, these formulas are going to be very, very helpful to you. Okay, now let us do some questions. Some 3-4 questions are there. After those questions, you're free to go. Free to go in the sense the class will get over. Sir, is it better to just memorize the proportionality, learn the derivation, and derive big formulas in examination hall? Sahil, see, if it is going to be a big formula, generally we are going to use it very rarely, right? So my suggestion is, if it is JEE advanced, you can have time to derive them in the exam, or roughly you can get to the answer, right? And in physics, there is no such thing which is damn big. If it is damn big, leave it. If it is something which is used very frequently while solving the questions, that you have to memorize. Nothing can be done, Mr. Sahil. Okay. The mean free path of molecules of a certain gas at standard temperature and pressure is 1500 T. Okay. Where D is the diameter of the gas molecule. While maintaining the standard pressure, the mean free path of the molecules at 373 Kelvin is, man, STP is going to be having a temperature of roughly 273 Kelvin. They are maintaining same pressure. For your kind information, just now I gave you some data that the mean free path is going to be proportional to T by P. They are maintaining same pressure. That means mean free path is directly proportional to temperature. So for this question, I can simply say that the mean free path is directly proportional to the temperature, right? In that case, lambda 1 by lambda 2 is going to be T1 by T2. Okay. Now they are asking the mean free path when it is 373. So let us take lambda 1. Lambda 2, let us take it to be 1500 D. Then T1 is 373 divided by 273. So your lambda 1 is going to be 373 divided by 273 multiplied with 1500 D. Multiplied with 1500 D. You can clearly see that 373 divided by 273 is more than 1, man. So more than 1 when multiplied with 1500 should be more than 1500. How many options have more than 1500? Not this, not this, not this, only one. So you don't even need to do the complete calculation. Don't waste time doing complete calculation. Now you have only 5 numericals. There is no options. There is no option given. Okay. Next question. An ideal gas is enclosed in a cylinder at pressure 2 atm and temperature 300 Kelvin. Pressure 2 atm and temperature 300 Kelvin. The mean time between two successive collisions is this much. That means relaxation time. If the pressure is doubled, temperature is increased to 500 Kelvin, the mean time between two successive collisions will be close to. They are talking about the relaxation time. Okay, let us go for the relaxation time. Relaxation time is directly proportional to root T by P. Is directly proportional to root T by P. I didn't get you, Vishal. Sir, we didn't bring any constant while taking out the proportionality. Anyway, the constant will get cancelled out because of ratio, na? We are talking about lambda 1 by lambda 2. So you can say lambda 1 is C T1, lambda 2 is C T2, C gets cancelled. So we don't need to bring any proportionality constant. Anyway, it gets cancelled. Okay, fine. For this one, the relaxation time is directly proportional to root T by P. Is directly proportional to root T by P. Okay. Now look. Tau 1 by tau 2 is going to be root T1 by T2 into P2 by P1. Right? So now, if I am going to take tau 1 as 6 into 10 to the power minus 8 by tau 2, then T1 is the initial temperature, which is 300, divided by final temperature, which is 500. P2 by P1, P2 is the second pressure, that is pressure is doubled. So if the pressure is doubled, obviously P2 by P1 will be this. Then the tau 2 is going to be what? Is going to be 3 into 10 to the power minus 8 root 5 by 3. Root 5 by 3. Root 5 by 3 is roughly 1.66. 1.66, you can say 1.3. Roughly 1.3 into 3, 3.9, close to 4. Yes, close to 4. Close to 4. Okay. Okay. Next. This. A 25 into 10 to the power minus 3 meter cube volume cylinder is filled with 1 mole of oxygen gas at room temperature. The molecular diameter of O2 and its root mean square speeds are found to be 0.3 and 200 respectively. What is the average collision rate for an O2 molecule? So bad. So bad. Right? They gave the RMS. From the RMS, you have to calculate the average also. So if this question, if these kind of things are going to come now, so bad. So bad. Okay. Mean free path is 1 by under root of n pi d square, number of molecules per volume, and they gave 1 mole. 1 mole means Avogadro number molecules in how much volume? In this much volume. Now look, I should actually go for V average. I should actually go for V average. If you are going to go with VRMS also, your answer will not be changing much because they are talking about powers. They are talking about powers. Okay. Still, we will try to go with proper way only. N pi d square into V average, right? Which is going to be root 8 RT by M naught. This is what you have to calculate, man. So bad. Who is going to do this in examination? But still, roughly you can do and get the answer. For your kind information, root 3RT by M naught is given as 200. So RT by M naught can be taken as 200 divided by root 3. So from here, this part is going to be root 8 by 3 into 200, right? And what about this one? This one is number of molecules per unit volume. 1 mole means Avogadro number 6.023 into 10 to the power 23 divided by 25 into 10 to the power minus 3. D is also given, nanometer. You know everything. Put it, get the answer. You know everything, put the values and get the answer. This is one of the worst questions I have come across. Who will do this calculation, man? And that too, you see, 10 to the power 11 is given, 10 to the power 10 is given, 12 is given, 13 is given. Come on. When you see these kind of calculations, my sincere suggestion to you is that mark this question, write it in the scribble pad. Come back to this question at the end of the paper. That is in your second round or in third round of the paper, you come to this. This will consume a lot of time and there is high possibility that you will make a calculation mistake and you are going to end up with a wrong answer. You will waste time and at the same time you are going to get negative marks to it. So when these kind of things are going to be coming up, leave it, move to the next questions. That's the reason why I picked it. Second, this is a bonus question. This is bonus. It's a wrong one. No answer is going to match. No answer is going to match. Two gases, argon and xenon, atomic radius and atomic weights have been given, have the same number density and are at same temperature. Ratio of the respective mean free path times is close to. Mean free time, not path. That means relaxation time. So tau is going to be what? Lambda by V average. What is lambda? 1 by under root of n pi d square. And V average root 8 RT by M naught. Now look, they said that the same number density and same temperature is there, right? So number density and temperature are same. Gas constant is anyway same. Pi is going to be anyway same. Root 2 is going to be anyway same. Now, if you want the ratio of argon to that of xenon, then you can clearly see that molar mass is directly proportional. It is in the under root, right? When it is going to go up. So it is going to be molar mass of argon to the molar mass of xenon and then diameter in the denominator. So it is going to be diameter of the xenon by diameter of the argon square. Diameter of the xenon and diameter of the argon square. Now looked, when we try to do the calculation, under root of argon is how much? 40 by 140. What about the diameter? Diameter of xenon, it is point, anyway radius is given. Diameter ratio or radius ratio, both will be same. So it is 0.1 divided by 0.07 square. So bad, so bad. Right, this is going to be root 2 by 7 multiplied with, you can say 10 by 7. So it is going to be 100 by 49. You can say that. So 100 by 49 into root 2 by 7. So when I am going to talk about root 2 by 7, it's roughly 0.3. Roughly 0.3. So which square will give you roughly 0.3? 0.6. Some 0.5 you take. Roughly 0.5 or it's in between 0.5 and 0.6. Let us take it to be some 0.3, right? So let us take it to be some 5.5. 5.5 into 2. like 0.55 into 2, which is going to be close to 1 something. There is nothing which is close to 1. There is nothing which is close to 1. That's why it was given as bonus. That's why this thing was given as bonus. Okay, right? With this, we are done with KTG. We are done with KTG and we are left with thermodynamics, and I will be covering thermodynamics in the next class. Sir, is it necessary to study magnetism for JEE mains? Are you talking about moving charges and magnetism, or you are are you talking about Biot-Savart, Ampere circuit and all those things, or Earth's magnetism, those things? If it is Earth's magnetism and those things, if you plan skipping, it's fine. It's fine. Harshita is asking, sir, can you say important lessons in physics at the last? Okay. See, the easiest ones and high weightage ones are going to be dual nature, atomic physics, nuclear physics, semiconductors, electromagnetic waves. These are the easiest ones. So you have to do those chapters first. Units and dimensions, errors, those are easy ones. You have to do them first. That's it. First you complete them, and then you can concentrate on SHM, waves, wave optics, ray optics, KTG, thermodynamics. If you do these many easily, you are going to get 50 marks. If you do these many easily, you are going to cross 50 marks. Wave optics, actually we were thinking of doing wave, like I am supposed to do wave optics next Tuesday, but there is some clash in the timetable. I have to see. There is some clash in the timetable, because from next week onwards in Vedantu Telugu JEE itself, I have to spend a lot of time. So I don't know whether I will be able to afford to give some amount of classes to JEE English, because I will be completely packed in Telugu itself. Till now, somehow I am managing, man. For example, afternoon 2:30 I started teaching. Now it is what, around 8:30, and teaching on YouTube is way different than offline. Why? One way, right? So I have to continuously talk, blah 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 blah, blah continuously. So you get exhausted. So we have to see. We have to sit and talk. Based on that, we will decide, because it's what we call too hectic. Too hectic. Okay, man. Bye bye. Good night.